Hello everyone, welcome to this video where I will demonstrate a bit of test-driven development in LabVIEW. So my name is Anton Sundqvist and I recently watched Tom McQuillan's channel here on YouTube where he has a video where he creates a snake game in LabVIEW using object-oriented design. I'll link to the video here below, and he really goes through the design process, starting with a UML diagram and then developing his classes and wiring it all together to complete the game. I thought that this was quite a fun little exercise, and in this video I'm gonna demonstrate how I work in LabVIEW using test-driven development. You will see that my approach is quite different, and especially regarding the design process. This video is not meant as a lecture, it's not scripted, it's probably not the best demonstration or lesson on test-driven development, but you should see it as a demonstration of the workflow, and hopefully there will be some good takeaways. So I guess most of you are familiar with the classic game of Snake. In Snake, the player controls a snake which moves across a board. The snake wants to eat. There's food randomly spawning on the board, and the player should control the snake so that it eats the food. And when it eats the food, it grows, and the game ends when the snake hits itself. Alright, so let's get going. I already set up a Git repository where we'll save our work. So let's go ahead and create a blank project to work from. So I'm gonna use object-oriented design here, but you will not need to understand a whole lot about object-oriented design in order to follow here, because it's not really important to this exercise. And the key here is really the test-driven side of it. So, in the spirit of test-driven development, we will start by creating a test case. When we work in test-driven development, you always start by making a test case, which will fail because you haven't written the code first. So, you always write the test code before you write the actual production code. Then, when we have the failing test, we implement the feature or the piece of code that we need in order to make the test pass. And after it has passed, we refactor to clean up and improve the design and the structure of our code. After we have done that, we start over again with the next failing test, all the time keeping the previous tests passing. And in this way, we know that we always have the existing code in a working state while we develop new features. So let's go ahead and start by creating a new test. So at this point we will need to start making some design decisions because we will need to decide what we want to test first. So we are going to build some kind of game board where a snake will move about and eat stuff. And I'm thinking that all of these things that live in the world will need to be some kind of objects that are at least aware of their position. We'll see what responsibility the classes or these objects will have in the end. But I think we can start by creating something. I don't want to call it object because that's a bit overloaded. Let's call it a particle. So we write a test for this particle. So this is created for us, and let's just create a test from the template and let's remove those placeholders. So I want the particle to carry a position. I probably need to create a class first because as of now I have nothing to test. So let's go ahead and create a class. Let's call this one particle. And we'll save it here. Right, there we go, we have a particle. Now let's go ahead and create some kind of constructor. Let's get rid of all this. There. So I'm not going to use the error terminals here because we don't have really any errors that we need to handle in this game. So it's all gonna be a lot of maths, and we don't really need to care about the error cluster. So I'm just gonna reduce a bit of wiring for now. Alright, we have something like this. Let's save it. Let's call it create, and also name it so that we can see what it is at the block diagram. So now we have some kind of constructor which we can use to create a particle. We probably then want to give it a position when we create it. So let's just go ahead and create a cluster, and then we can just take some numerical controls. I'm going to use integers here because I imagine that our game board is going to be based on integers, pixels, what we want to call it. Call this one position, and we want to have a position in X, and we also need to have a position in Y. Let's just resize this one and maybe make it into type def, because I imagine that this is something that we're going to reuse a lot. And if you want to change it later, it's much easier if you have it as a type def. So let's go ahead and save it. So the type def is saved. Let's also save our project. And there we go. So let's call it snake game, like so. And then we also have our test method, which we will need to name now. Let's just call it test particle as position. We can rename it later because we don't really know what we're testing yet. So let's not put too much thought into that now. So we have this constructor, which we probably need to wire up the connector pane for to get the inputs. So create constants, let's give it a position when we create it, 2 and 3 for example, and now we probably want to test that the particle has the position 2 and 3. So how are we gonna get that out of here? Let's create an accessor. So the fastest way I can imagine is just to go ahead and add this one here and save this one, new from data member access, read position, and let's remove those. There we go. So now we have a read position method which we can save, and let's call it read position, like so. And now we can wire this one up to the constructor. There we go. And then we can test that we actually get the same position, and we can run the test. And I expect this one to fail because we haven't actually done any implementation yet. We have just designed the API for getting the position. So normally I would actually not write tests for getters and setters, but this felt like a good way to start. So let's not be too dogmatic about it. Now we have this failing test. The read position should work, but the constructor is not implemented. So let's go ahead and insert the bundle by name in there. So we run the test again, and now it should pass because, yeah, there we go. All right, so let's just close these down. Then we need to think about what goes next. So the snake, I imagine, will be its own class. Let's go ahead and call it snake. It's probably a good name for the class. There we go. And then we will need a test for the snake. Let's just create a new test case here as well. And we call it snake test. Probably a good name. And now we need to start creating some tests for the snake. And maybe we want to just make a constructor to start with. So let's make a constructor, and now we again need to think about our design a bit. So what are we actually going to test with this snake? So I'm probably going to be interested in ensuring that the snake is able to move, that it occupies some space, and has some kind of position. But as a snake has a length, and the shape, it's probably not going to be a single number for the position. So I imagine that it's going to be built up out of many smaller pieces, particles in this case. But we'll get to that later. For now, let's assume that we will need to check whether a snake is in a given position. And in order to do that, we will probably need to check if a snake can collide with a particle, because that's how we're going to determine if the snake is in a given position or not later. So let's go ahead and create, let's start with a constructor to get going here. Call it create, just to keep it similar to the other one. Let's change this to a constant, remove this one, and also the errors we don't need. Let's call this one create as well. So we have a constructor, let's place it here. Not that much going on yet, so we probably need to give it an initial position. So let's do that. Let's take the same type that we had here, wire it up, and we give it a position. Let's spawn it at 2 and 4, that's good. And now we want to make sure that if we have a particle in the same position, it will collide with the snake. So we probably need to have something to check for that. So let's call this one, create a new method and call it check collision. And we want to check if a snake has collided with a particle. So let's add a particle as an argument into this method, like so. Let's call it also check collision. Let's place it here, and there we go. Can also remove those. And that one. Alright, then we need a particle to check with, and that's pretty easy for us to create now since we already have the constructor here and we know that this one at least carries the position. We have already tested that. Alright, so we create a snake, give it an initial position, we create a particle, and then we check for collision. Okay, we need to get some kind of result out of this one. Probably we need to know if it collided. So let's check for that one, and then we want to have this one to be true. So let's make this one a pass if instead of a pass if equal. So let's wire the pass if into there. Alright, so this one should now fail because we haven't actually implemented. Oh, I haven't saved it either, so it doesn't even run. So that's good to check that we have saved it. So test snake initial position, maybe. Okay, let's give it another go, see if it passes, and there it fails, so that's good. So now we have our test here. We need to start thinking about the implementation. So probably we need to carry the position in some kind of way, and we also need to check for collision. So let's see how we are going to save this one. We could just save the position as it is into an argument for the snake. But as I said, I think we're going to make the snake consist out of particles. So maybe we just create a particle instead and have that one carry the position. So we delegate this to the particle, which we then compose into the snake here. Like so. There we have it. So now we have a particle within the class or the private data of this snake class. Then we can check the collision here. Then we have a particle in, and we have our own particle representing the position. So now let's just read the position of both of these and check if it's equal, because that's our criteria to know if it has collided or not. So now we get a cluster out of there, so I probably want to make that to an array, and then I want to make sure that all of the array elements are equal, so let's make an add array elements. So now if both the X and the Y position matches, we would get a true here, and we know that they collided. Also, this would, if we wanted to introduce a third coordinate and play 3D snake, this algorithm would still hold. But if it didn't, if we made something, a worse design, our test would then catch it later. So this is why it's very good to always have these tests of all the behaviors that we expect from our design. So let's now run the test and see what happens. And it passes, so that's good. So that's all good. And now we probably want to make something more interesting and make the snake move in some way. So let's, I think we're gonna have something similar to this one. So let's just copy this one, save it, and give it a new name. Test snake moves. Let's test it moving horizontally at first. And now we have the test case, we need to modify it in some way. So my idea here is that I start with the snake in position 2, 4, and then I will move it one step in the positive X direction, and then I expect it to be at 3, 4. So how do I do the moving? I probably want to be able to have the snake know about its velocity in some kind of way, and then I want to be able to make time steps. So each time step it will then move a tiny bit. I think that we would need to have some way of changing the snake's velocity, so that would mean accelerate it, or let's just call it move. No, let's call it accelerate. Accelerate, and let's make so we add the accelerate into here. So also we need to maybe specify in which direction we want to accelerate. So that would probably be well carried by an enum. So let's call this direction, and then we need to have some kind of options to choose from, and in 2 dimensions we would have an x minus x, y, and minus y. Let's wire up this one, and we accelerate it in positive x, and then I expect the x coordinate to increase. As I said, I probably want to make a time step so that I can keep the position and then make many time steps to have the snake travel around. So let's also make a method for that. Let's call that one time time step. And yeah, this one we could probably make more general later on and have other objects in the world implement to be able to time step many things in the world. So we could have enemies or something moving about. So I think that's it. We have our test case here. We start by creating a snake, we accelerate it, and then we take the time step and expect it to be at this new position, which is then 1 greater in x direction and the same y direction. So we need to implement this in some way. Let's just remove all this, and I think we need to make sure that the snake carries the position in as an argument. I think we probably want to make that a type def, because we want to add it into here. Where did it go? Open type def and save it. Call it direction, that's a good name for it. And now we go ahead. Where did you go? There is our snake. Place the direction into here. Now we have a starting direction, and that's probably fine for now. Let's not care about that, because that's probably something for later. So let's make our direction go into here. Save this one. So now we have the acceleration, or we have accelerated it. So now we know in which direction we move. Then we make the time step, and really we could have made it even simpler, but let's see. We have our particle, which represents the position, and we could read the position from the particle using this accessor that we made. Let's unbundle what we read from it. Let's again get rid of those, and let's increment the X position into here. Particle, yeah, now we need to create a new particle in order for this to work, because this is the only way to assign the position to a particle. Once a particle in this way has been created, it cannot really move, it's static. So we basically throw away the old one and replace it with a new one. And I think this would make the test pass. Let's have a look. Did I save it? No, I didn't. Yeah, so it does move, and I actually forgot to run it before to see that it fails, but we can just destroy this one and run it again and see that it actually fails. So yeah, I'm pretty confident with this. I don't need to start over. So you see that this is quite a, well, let's say bad implementation, because when we do a time step, we will move in the positive X direction regardless of in which way the snake is accelerated. So we probably need to do something more interesting. So let's create a new test here. Let's call it, let's move the test snake moves negative horizontal direction. So if we then move in the negative X direction, remove that one, create constant negative X, like so, then we would expect this one to be 1 instead, because we start at 2, move 1 back, and then we get to 1. Let's save everything, run the test, and see that it does fail. There we go, it fails. And that's obvious, because here we always move in the positive X direction, even if we were not moving in the X direction at all. So now we need to do something more interesting. We need to take the direction information from here, and we need to make this conditionally. Let's just make it a bit tighter, take it from here instead, like so. And if we are in the negative X, this would then be a decrement. We have X, let's delete this one, copy or duplicate this one. This would then be the X case we increment. Let's add case after, make it default just to make it compile, wire this one over, and now we should be able to move in both positive and negative X direction. We'll handle the Y directions later, and this is part of the process that we only focus on one bit of the puzzle at a time, and then we incrementally work towards a solution. So now when we run this one, it should pass, because we handle both positive and negative horizontal directions. And once that works, I think it's time to move vertically as well. So let's go ahead and create another test case. And this is not the one I want. I want to have one of these where we move. Let's save this, add it to the snake test case, and let's call this now test snake moves vertically. And now let's start again at 2, 4. We move in positive Y direction, then X should be as it was, and Y should increase. Always just checking where we are by colliding with the particle statically at that point. Let's save everything, and this one should now fail because we haven't implemented the Y direction move yet. That's it. Let's go ahead into time step where we had this piece of code. Let's just duplicate this one Y like so, and we can also take the negative Y now at once. So I'm not overly afraid of making a mistake here, and if I did, I will catch it later. So for now, I'm actually going to skip writing a test for this one, and this is a bit of a pragmatic choice. I could decide to test everything, but I assume that I get this correct now, as it's such a small change. And there we go. Now we can move vertically as well, and we haven't tested the negative vertical direction, but I'm pretty confident with this one. So now we have a snake which moves around. Then we can go ahead with the next piece, and when we control the snake, there is some constraints on how it actually can move. So if we are moving in the positive x direction, we can't turn around 180 degrees and start moving in the negative x direction. That would mean that we go into ourselves, and as I remember it from the good old days when we played on the phone, this was not possible to do. So let's make a test case for that. We have the snake test. Let's create maybe from move vertically. Now we can maybe at the same time test the negative vertical as well. So snake cannot reverse. And as I have no coverage for the negative, let's start by moving in negative y direction, make a time step, and then if I accelerate it in the positive y direction, I actually want it to continue in the negative direction when I make the next time step. So I don't want this to do anything if we are trying to reverse the direction which we are traveling in. So I mean, if we put a y in here, like so, we should, after this time step, we should be at 3. So we go from 4 to 3, then we accelerate it, but this doesn't do anything. So another time step should bring it to 2. So now it should go into here if I told this correctly. So let's just run this one and see what happens. And it fails. So in order to pass this test, we will need to filter out our commands so that when we demand an acceleration in the positive y direction, we only accept it if we are not moving already in the negative y direction. So let's go into this, accelerate VI. This is probably the best place to implement it. And let's have a look at the direction we are going. We want to do something conditionally on the direction. We place a case structure here, use the direction as selector, and then if we go in the negative y direction, we would check if the new direction is equal to y. That is when we would filter it out and continue to move in the direction we were coming from, like so. And if we are choosing something else than y, then we could just go the direction that we chose or continue that one. Let's see, let's delete this one. Let's duplicate this one, make it default, just to make, so I want to make it compile so that I can run my test. Let's remove everything here from the default case. Let's get rid of that wire, like so. So now we only take care of this specific case, and let's run the test and see, and I expect it now to pass. There we go. So maybe we can make some more tests for this reversing. It's quite simple to make the test cases here. Cannot reverse in X, or let's call it horizontally. So let's say that we move in the positive X direction and we want to start moving in the negative X direction. So we go one step from 2, that is 3, and then we try to go backwards, but we can't, so we continue to 4. And we were at 4 in Y, so we keep that position. Let's see, this one should now fail. Oh, let's maybe save it first so that we can see it run. And there we go, it did fail. That's good. Then we can go ahead and implement these cases. So let's delete this default case again. Let's duplicate this. So for y, we want to filter out negative y. For negative x, we want to filter out x. And for positive x, we want to filter out negative x. So that's it. And let's see what happens if we run this test. Yeah, now we have a new fail here. Let's have a look. Snake can't move in snake moves negative horizontal direction. Oh, this is quite interesting, because our initial velocity was positive x. So now when we try to move in negative x, it fails because we can't do that. So now we have two requirements that clash with each other, or two tests that can't simultaneously be passing. So either we would delete this one, or we would re-implement it in some kind of way. And I think we could just improve it a bit by making a few more steps here. So let's put accelerate in here. Let's move it in positive y. We need to take a time step after that. Time step. And after that we go in negative x, and then this should then work. So we will increment our y coordinate from 4 to 5, and then we'll decrement the x coordinate from 2 to 1. So let's see if this change now passes. And it does. So now that we have all our tests passing, let's think about what to do next. So now we have a snake which can move, but the snake is only 1 pixel large, and in this game the snake will grow by eating food. So let's test this in some way. I think the next thing we want to test is really that the snake can eat, and what happens then. So let's maybe start from scratch again. New VI, or new from template. Test snake can eat, or snake eats. Well, we can call it what we want. So we really want to have a snake created. We then need to make it eat. So we probably need a new method for that. Let's create a method here. Call this one eat. So when we call eat on the snake, it eats. And what we will see then when it eats, or what we wish to see if this works, is that the snake grows in size. And we start this at 2.4, that's good. And how can we know that it has grown in size? Well, we could check for collision again. This is how we probe the snake here. So what should we check for? We should probably take a time step as well. And to make sure that we know in which direction it moves, we could also make it accelerate. So I'll make it accelerate in the positive x direction. This doesn't really change anything as of now, because the initial direction was already x, but if I change that later, I don't want this test to fail. So it's always good to have a setup which we control. Right, so we accelerate it, we move in the positive x direction, we eat, we take a time step, and now I expect my snake to have a head and a tail, and I want to check that the head has moved 1 position. So the head will have moved to 3, 4, and I think the neatest way to make this look visually is to have the snake's tail grow after it, so the snake always gets longer backwards, so to say. So let's make sure that the tail then stays at the initial position here. So we want to make sure that the snake occupies these 2 coordinates. So we have 2 positions that we check for. Let's add another pass if equal, or actually pass if, pass if, and make this one also into a pass if. Again, I'm not overly careful with the error wires. So when I run this test, I expect it to fail. Let's see what happens. Snake can eat, it fails. The first one passes and the second one fails. Maybe you should add some more descriptors here to make it more clear. So here we are checking the head. Let's just do like so, head and tail. And then when we run this, we will have some more information here so that we can figure out what did fail. So the head passes and the tail failed. Good. So now we need to change the implementation of the snake. We have this eat method which does nothing. We can remove some scaffolding here. And we also have the snake which is represented by a particle. Now I expect that we will need to have an array of particles. So let's change this one to an array and let's call it body of the snake. That's good. Now we probably have a lot of compile issues of a time step which does not work. So I think that the time steps is probably going to work if we just make this into a for loop and iterate over all of our body parts. So each body part, no, it will not, because we are not supposed to move the whole snake. Because if we had a snake which were vertical and we moved in the next direction, it would move sideways. That's not what we want. What we want is to only remove the tail and place it at the head position. So this should be quite straightforward. Basically, we want to just delete the tail from the array and take the head, which we move. So we move the head and delete the tail, and then we just build a new array out of this. So we add the head at the start of the array and we add the tail after it, like so. So here the tail with the last element deleted. And then we see that we have a compile error here as well, and that's of course because this was now an array. And I'm happy with just looping over the array and checking all of the pieces of the snake, because if any piece of the body hits the particle, it should fail, or it should collide. So let's just go ahead and make this one indexing, because we want to check all of them. And then if any of them hits, it should be collided, should be true. So let's insert an OR here, or array elements. Like so, and then we have one last compile error here, and that's of course because this now needs to be an array. So now we have an array of particles and we start with 1. Like so, and let's save everything. Let's see what happens with our tests if we run them. And now we have made quite a big design change here. We have changed the implementation of the snake from carrying only a particle to be an array. And we can see that we didn't actually break anything. Everything works just as before. And this is one of the very big benefits of having the test scaffolding here to support us, so that we can with confidence make these kind of design changes without being too afraid of breaking anything. But we haven't actually implemented this eat function yet. And let's go into the eat method, and we need to figure out something to do here. So the snake will only need to be able to eat once per time step. So I think it would make sense to have it set a flag during the eat. So let's just create a flag for it here. Let's call it has eaten. And this would then be if the snake has eaten during this time step. So of course if we eat, then this should be true. Alright, so if we then take a time step, and yeah, now if we have eaten, then we take out this one. We wouldn't delete anything from our array, we will keep the tail. So if we just make a case around this one as well, if has eaten is true, we don't want to do anything. So if has eaten is false, we delete the tail, and if it's true, we let it be. And I think that's it. We need to reset the flag. I should probably make a test case for that as well. Well, yeah, just for the sake of it, let's do. So let's see what happens with the current tests. At first, now it passes, everything is green, that's good. And now I said I wanted to create a test to make sure that if we eat once, it doesn't continue to grow. The snake stops growing when it takes a time step. So test snake grows only once after eating, like so. So here we now want to take another time step. We add it there, and we want to make sure that it doesn't collide here. So we don't need to care about this one. We don't need to care about where the head goes. Remove that. And this is now misleading. So let's remove that as well. And this should not be a fail if, because if we are still here, that means that the tail is continuing to growing. We just grow into infinity. And this should now fail because we haven't reset the flag in there. And there we go, it fails. And as I said, I think this is because we need to reset this one as false. And then when we run the test again, we can see that it passes. Alright, that's all good. So now we have a snake which can move and eat, and I think we have one thing left to do for the snake. It needs to be able to die, or we need to know if it's alive. So if it hits itself, it should die. How would that look like? Let's maybe make some kind of predicate here to check snake is alive. Alive, and let's just make it output alive, like so, and we call this alive, like so, and let's just copy this one to start from. This snake not alive after collision with self. So this is going to be quite elaborate because we need to make the snake first grow into a length which is enough for it to collide with itself, and then we need to make it move in a circle to hit its own tail. So to do that, let's first have it eat some. So we move in the X direction, that's fine, we take it. We want to eat, like so, and we want to do this a few times, so maybe we do it for 6 times. And then we start moving in a circle, so we don't need that one anymore, and we don't need this one. We can delete that one, like so. And let's take this one, let's replace eat with accelerate and create some constant, make this into an array, and then we move the positive x, we take one step in the positive y. This should of course be indexing. So yeah, positive y, then we go in negative x, and then negative y, and those take a time step in between. So here we first eat, and then we circle back, and we hit ourselves, and then we assume that this would not be alive afterwards, so this should be fail if. And now I actually think this will pass, because we haven't actually tested that the snake is alive. There we go, it passes. So we need one more test. Add snake alive when created. So now we want to remove all this and pass if save and then run the test, and this one should now fail because alive is just the default value of false, so it fails. Alright, so this is quite a simple one to fix. We just make sure that when we create the snake, it needs to be alive, and how do we know that it's alive? It needs to carry the state with it. So let's just make another flag in here. Alive, like so. Save it in there, save, and make this one snake is created alive. Now this second test we created should pass, but the first one should now fail because we haven't actually made the snake die. But it doesn't. This is interesting. See, I forgot to implement this. And this is part of the process. This would have been a quite nasty bug to hunt down later, but because I went through the process of creating the test case here, I caught it this soon, and it took me a second to realize that I made a mistake. And now we run all the tests again, and there we see we get the fail as we expected. So let's go ahead and see how can we make the snake die. So it's probably during the time step. We are gonna check if the snake head, we only care about the head, right? So if the new head here, this is the new head which goes on top of the body, if this collides with any part of the body, then the snake dies. So we could just use the method we had here earlier. We could take check collision, maybe like so. So we take the snake, this is a method on the snake class, so it takes a snake as the argument. Clean up, we check it for collision with the head, but this is not what we want to do, because this will then check for a collision with the whole snake, and the head will of course collide with the head. So we actually want to take the old snake if you follow, we want to take the old snake where the head was what will now be part of the body, and then we check if the new head collides with the old snake, then this should it should be a collision, and then the snake should not be alive. So if collided, it's not alive. So let's see if we got this one right. And yes, it passes. So that's all good. The snake has died. So yeah, what happens when it dies? I think it would make sense for it to stop. So let's see if we take this one where we already have it not being alive. Test snake does not move when not alive. So now we need to do a bit of logic here. So we start at 2, 4, we move 6 steps to the east or to the right. That should make us be at position 8. Then we go 1 in the y direction, that makes this one 5. We go 1 in the negative x direction, we're back at 7. And then we go 1 in the negative y direction, so that's 4. And if the snake continues to move in the negative y direction, it's at 3, alright. So basically we want to make sure that it's not at this position, because that means that it continues to move. So let's check for collision. This is how we do it. So we create a particle, we check if the particle has collided with the snake, and it should fail if it collides. So let's see what happens if we run this. So it passed. That means that I made a mistake in my logic here, and let's just probe this one, run it and see. The snake's head is at 7.4. That's because I did not take the last time step. So I actually did not take any more time steps after the collision. So what about now? There we go, now it fails. That's all good. So now we must make sure that the snake doesn't move if it's dead. So that the logical place to do this is probably in the time step, and we check for alive, and we basically don't need to do anything unless the snake is alive. So if the snake is alive, we do this stuff, and if it's not alive, we do nothing. And I'm pretty sure that this should now work.